Hello guys, in this lecture we will discuss about the working of an induction motor, and also we will try to understand how to torque produce in any induction motor. As we know that induction motor is a singly excited AC machine, and induction motor divided into two parts. One is a squirrel cage induction motor and another one is wound rotor induction motor. Before we start the explanation about the squirrel cage induction motor and wound rotor induction motor, let's we discuss about the torque production of an induction motor. See what happened in an induction motor. Let us assume that the stator magnetic poles like North Pole, South Pole, North Pole and South Pole. Okay, stator is nothing but it is a outer part of any induction motor where we supply the AC voltage. Okay, and this magnetic pole, it will assume the magnetic pole in an stator or in stationary part. Okay, when we supply the AC voltage to the stator, due to which the rotating magnetic field is produced, this magnetic field is produced by the supply voltage of an stator. Okay, the rotating magnetic field is also called a synchronous speed, which is denoted by ns. Synchronous speed is nothing but it is basically the conversion of electrical frequency in mechanical speed in terms of RPM. This is called a synchronous speed, or we can say rotating magnetic field. Let us assume that the rotating magnetic field is rotate in anti-clockwise direction. See, the direction of the rotating magnetic field is in anti-clockwise. See, this is the direction of the rotating magnetic field. The direction of the rotating magnetic field is in a anti-clockwise direction. Okay, now what happened at a standstill condition, the rotor conductor is stationary. The rotor conductor has been placed in a rotor body of an induction motor. So at standstill, or we can say at a stationary position, the rotor conductor is not rotate, but its rotation could be assumed that in opposite direction or in clockwise direction. Let us we will try to understand how rotor conductor rotate could be assumed that in clockwise when it is already at a stationary position. Okay, for example, Rohan, this boy name is Rohan. For example, Rohan is standing on the railway platform. Rohan is a stationary. Okay, Rohan is standing on the railway platform. Okay, and he is waiting for the train. And suddenly what happened? Train is coming. This is the train. And suddenly train is coming, and it is moving in forward direction. With respect to Rohan. or we can say, but Rohan is stationary. But Rohan is stationary, or we can say, if we assume that train is stationary, if we assume that train is stationary for some moment, Rohan is moving in opposite direction of train with respect to train. So what we are trying to say, if RMF or rotating magnetic field is rotate in anti-clockwise direction with respect to rotor conductor, this is the rotor conductor, with respect to rotor conductor, and when we assume that rotating magnetic field is stationary for some moment, it means that rotor conductor is rotating in opposite direction of rotating magnetic field with respect to rotating magnetic field. Like this is this clockwise direction is the direction of a rotor conductor. How can we assume that the rotor conductor is rotate in clockwise direction, or we can say is rotate in the opposite direction of the rotating magnetic field? That have already explained with the help of these example, the train and Rohan example. So keep in your mind that rotor conductor is, if a rotating magnetic field is rotating in anti-clockwise direction with respect to rotating magnetic field, rotor conductor is rotate in clockwise direction. Okay. Now, when we are talking about the conductor under the North Pole, and in North Pole, as we know that in North Pole, magnetic field goes out of the pole, and in South Pole, magnetic field or magnetic lines of force comes into the pole. Okay. Now, these cross and dot notation depends on the V cross B. How dot and cross notation will depends on the V cross B? Let us see. See, the conductor under the North Pole and the movement of rotor conductor under the North Pole is in this direction. This is the V, vector V is the velocity of the rotor conductor under the North Pole. And as we know that in North Pole, magnetic lines of force goes out of the pole. So the magnetic field direction, the direction of the magnetic field indicates the downward direction, the direction of the magnetic field indicates the downwards, like this. Okay, like this. Now, how can we notate dot and cross based on V cross V? Let us see. See, when we apply the right hand rule, our four fingers of right hand indicate the velocity of conductor, and when we are moving towards the magnetic field, and when we are moving towards the magnetic field, our thumb indicates the dot or cross. See, in this rotor conductor under the north pole, when we are moving our four fingers towards the magnetic field, so our thumb indicates into the screen or into the paper. When our thumb indicates into the screen or into the paper, that notation is called a cross notation. And when our thumb indicates out of the screen or out of the paper, that notation is called a dot notation. So cross and dot notation depends upon the velocity of the conductor or magnetic field. With the help of this, we can easily identify whether the conductor is dot notation or whether the conductor is cross notation. Okay, so the conductor under the north pole is a cross notation, and similarly in opposite pole or south pole, the rotor conductor notation is dot pole. Again north pole, the conductor notation is cross, and again south pole, the conductor notation is dot. This is the way of how can we dot and cross notation notify based on V cross B, or velocity of the conductor and magnetic field. See, in cross notation, magnetic lines of force, the direction of magnetic field is an anti-clockwise direction, or in dot notation of the conductor, magnetic lines of force or magnetic field is in anti-clockwise direction. So always remember and always keep this point in your mind that the magnetic lines of force is in the clockwise direction when we are talking about the cross notation, and when we are talking about the dot notation, the magnetic lines of force is in the anti-clockwise directions. Okay, see, in this region, how can we denote this rotor pole is a south pole? See, when magnetic lines of force comes into the pole, that is called a south pole. So in this region, the magnetic lines of force come into the pole. And again here in this region, this rotor pole is called a north pole. Why this rotor pole is called a north pole? Because we know that when magnetic lines of force goes out of the pole, that is pole, or goes away from the pole, that pole is called a north pole. And in similar manner, this is south rotor pole, and this is north pole, rotor pole. So this is the way of rotor poles induced in an rotor of any induction motor. And due to this, when stator south pole or rotor south pole, these two like poles are repel each other, and again this rotor south pole and this stator north poles, opposite poles, are attract each other, and again this and again this north pole and this north pole are repel each other, and again these north pole and these south pole, opposite poles, are attract each other. So this is the way of torque produced in an induction motor. So the direction of torque produced in an induction motor is in the anti-clockwise direction. So this is the arrow. This arrow indicates the torque production in a rotor of an induction motor. So this is the way of torque produced in a induction motor. As we discussed at the starting of the lecture, that induction machine is divided into two parts. One is a squirrel cage and another one is wound rotor. So in a squirrel cage induction motor, the rotor has conductor just like damper bars, and as we can see in figure A, same number of poles are induced in the rotor as the stator, which is an essential condition for torque production. So my dear friends, always remember these points and always keep these points in your mind, that for any induction motor, what condition is essential for torque production? That is, the same number of poles are induced in the rotor as the stator, which is an essential condition for torque productions. So this is the important point which should have remembered in case of induction motor, that the poles of the stator poles is always equals to the poles of the rotor poles. See, in stator poles there are 4 poles. Similarly, in rotor poles it will induce a 4 pole also. So when rotor poles and stator poles is same, then it will produce torque. Otherwise, if number of poles on stator will not equal to the number of poles on the rotor, that it will not produce any kind of torque in an induction motor. So this is the essential condition for torque production, that the number of poles are induced in the rotor as the stator. Next, in wound rotor induction motor, winding on the rotor should be such that the same number of poles are induced in the rotor as the stator. It will fulfill the essential condition, that we need to winding arrangement on the rotor that should be such that the same number of poles are induced in the rotor as the stator. Whenever current reverses its direction, a pole is induced. So in wound rotor, the winding should be designed such that current reversal takes place as many number of times as there are poles on the stator. Now next, let us see how torque rotation take place in an induction motor. This is the way of torque production in an induction motor. As we discussed earlier, that torque is produced in a anti-clockwise directions, and also uh, we assumed that the rotating magnetic field is rotate in anti-clockwise. So in an induction motor, torque is always produced in the direction of the rotating magnetic field. Okay, the torque is produced on the rotor in the same direction as the rotating magnetic field, because the torque tries to reduce the relative speed between stator and rotor. And see, this is the stator current. Stator current is the resultant of the rotor current and magnetizing current. Okay, and the stator current is the resultant current of rotor and magnetizing current. So this is the way of torque production in any induction motor. So as we can see in the GIF of the rotation of an induction motor, torque is produced on the rotor in the same direction as the rotating magnetic field, because the torque tries to reduce the relative speed between stator and rotor. Now, if rotor speed is nr, stator field speed or rotating magnetic field speed ns. So the relative speed is ns minus nr. This is the speed between the rotating magnetic field and rotor conductor. Okay. Now due to the air gap between stator and rotor, see this portion, this is the portion, the stator, in between the stator and rotor, the air gap is here. In between the stator and rotor, the air gap is take place, and due to air gap between stator and rotor, the entire flux of one winding does not link with the other winding, and there is some leakage flux which is represented as leakage reactance in the equivalent circuit, and hence the current should lag behind the EMF by a certain angle. So in this phasor diagram, the torque is produced in such a direction that the rotor MMF tries to catch the stator MMF in order to make an angle between them 0. So in this phasor diagram, the rotor EMF is lagged behind the stator flux by an angle 90 degree, or due to air gap, the rotor current lags behind the rotor induced EMF by some angle like theta 2, and synchronous speed is in anti-clockwise direction. So in the same direction, electromagnetic or torque is produced. Okay, so lambda is 90 plus theta when we are talking about the angle between the stator flux and rotor current. The lambda is the angle which is equals to the 90 plus theta 2, and torque is always proportional to the sine lambda, which is the angle between the stator flux and rotor current. So this is the basic principle or basic working of any induction motor. In this lecture, we discussed about the torque production of an induction motor, how torque is produced in any induction motor, and what essential condition should be remembered or should be should be remembered for torque production. Okay, when number of stator poles is equal to the number of rotor poles, if it is equal, then the torque will produce, otherwise it will fail to create a same number of poles, or we can say to induce a same number of poles in the rotor as the stator. That means there is no kind of torque is produced in an induction motor. So guys, these all about the torque production of an induction motor. I hope you are enjoying the video. So guys, thank you very much.